we're going to talk about the ideal gas law in this video. In order to do well with this topic, you'll want to make sure you've reviewed pressure, temperature, volume, moles, and unit conversions. The ideal gas law is pretty much a summary of all the relationships that we know about pressure. So we know that pressure and volume are inversely proportional, and that pressure and the number of moles, that would be, that would be N here, that's the number of moles, are directly proportional. See how they directly proportional? And pressure and temperature are directly proportional. There's T. And then we have this other piece here, which is R. And R is the gas law constant. And it's in there to make sure the whole model works, because really mathematical equations are just models, and we want to make sure that they accurately predict what's going to happen. And in this case, we want to make sure they accurately predict what's going to happen to pressure and volume and the number of moles and the temperature. So since R is a constant, it's 0.0821 liters times atmospheres over moles times Kelvin, which is a really big chunk of units right there. Now, the good news about that is that, well, first of all, I would give you R. You don't have to memorize it on an exam. And second of all, these different units here tell us what our units need to be in when we do a problem of this type. So if I'm going to use this equation, then I have to make sure that my pressure units match the pressure units in R, which are atmospheres. So these guys have to be in atmospheres, and my volume has to be in liters, and my number of moles, well, there, moles. And the temperature has to be in Kelvin. And in fact, there's a couple of different ways we'll solve ideal gas law problems, and sometimes the atmosphere and the pressure can be in different units, but the temperature is always, always, always in Kelvin. So there's two scenarios that you'll encounter, or two types of problems really, that you'll encounter with the ideal gas law. In the first scenario, you are given one set of information about a gas. You get one temperature, one volume, one number of moles, and or one pressure. And you're essentially asked to solve for the missing variable in the gas law. So we might be given the pressure and the volume and the number of moles and asked to find the temperature. So that's our first scenario. Our second scenario is you have one gas that undergoes some kind of change. And in this case, you have an initial set of values for the gas followed by a completely new set of values after something is changed. So in this case, we might have a first pressure and a second pressure, and a first volume and a second volume, and maybe a first temperature, and we will be asked to solve for the missing final temperature of the gas. So let's talk about how you would solve each of these. Looking at number one, this problem, when we read it, gives us one set of conditions for the gas and asks us to solve for a missing variable. So it says how many moles of gas are present in a sample of nitrogen gas at 25 degrees Celsius, 790 millimeters of mercury, and present in a 500.0 milliliter container. Lots of information here in this problem, and to help us organize our thoughts, you might want to just list everything out in an ideal gas law. So I'm going to write my ideal gas law equation up here to remind myself of what those variables are, and then I'm just going to list them down here. We know what R is. It's a constant, so I don't need to list that, but sometimes it's helpful to remind yourself. And then I'm just going to identify where things are. So here's my pressure, because I have units of pressure, millimeters of mercury, 790.0 millimeters of mercury. And my volume is this 500 milliliters. And my temperature is 25 degrees Celsius. And it asks me for how many moles of gas. So there's my question mark. And I know that R is 0.0821 liters atmospheres over moles times Kelvin. So the first thing I want to do is check and make sure that everybody's units match R's. So I can look at my pressure units and see, millimeters of mercury, but down here in R, my pressure unit is atmospheres. So I need to change millimeters of mercury to atmospheres. So 790.0 millimeters of mercury. There are 760 millimeters of mercury in 1 atmosphere. So I can set that up and plug it into my calculator. And that gives me 1.039 atmospheres. Notice I'm carrying more, well, actually I didn't carry more significant figures than I need, but I will in general carry more than I need at the end. And now I'm going to look at my volume and see this is milliliters, but whoops, down here it's liters. So 500.0 milliliters, change to liters, gives me 0.5000, keeping all my significant figures there. Temperature is given to me in Celsius, but I need to have it in Kelvin, and in fact, anytime we do an ideal gas law problem of any kind, Celsius always gets converted to Kelvin. So Celsius to Kelvin is just 25 plus 273, and that gives me 298 Kelvin. Now I'm ready to do some algebra. I need to solve for my variable, and so I'm just going to divide both sides by RT to move everybody over to one side. So I end up with N equals PV over RT. And now I can take this information that I have and plug it in to my equation. And now I've just managed to erase all, or excuse me, to remove any space that I had to do this. We'll see if we can do it up here. So we know N equals my pressure, which was 1.039 atmospheres, times my volume, which is 0.5 liters, divided by R, 0.0821 liters, atmospheres, moles, Kelvin, all that times my temperature, which is 298 K. Now, I am noticing here that my units can cancel out, liters and atmospheres and Kelvin, and I'm left with moles, which is good. That tells me I'm doing my math correctly, my algebra correctly. I plug all those numbers in, put them into my calculator, and end up with an answer of 0.0212 moles. Now, a word here about significant figures. It may look like in the problem that I only had 2 significant figures in my temperature, but when I change temperature from Celsius to Kelvin down here, I ended up with 3 significant figures, and that's the number that I used in my equation. So therefore, my answer should have 3 significant figures. So my answer is good to go. All right, let's look at the second type of example. In this case, I have 345 milliliters of gas at 1.2 atm is placed in a 1.15 liter container. What is the new pressure of the gas? I see a volume initially and then a second volume. So I have V1 and V2. I have an initial pressure of P1 and a new pressure P2 that it's asking me for. So V1 is 345 milliliters, V2 is 1.15 liters, P1 is 1.2 atmospheres, and P2 is, hey, we got to figure that one out. So to tackle this problem, you have a couple different choices. You could memorize the individual gas laws, Charles' law, Boyle's law, Avogadro's law. You could approach it that way. Or you could say, and I don't really like to memorize things for the sake of memorization, so I'll do it this way, where I take one ideal gas law and I ratio it to a second ideal gas law. And when I do that, I can cross out what stays constant. Now, in this scenario, what stays constant is the stuff that I don't know anything about. So it didn't tell me anything about the number of moles, and it didn't mention temperature. So I can safely assume that those stay constant. And if something stays constant, then that means it doesn't change. So my N1 and my N2 values will cancel each other out because they're the same number. R is a constant, so it doesn't change. And my temperature in this problem doesn't change either. So I end up with P1 V1 over P2 V2 equals 1. And I actually want to solve for P2, so I just need to multiply both sides by P2, and I will have P2 equals P1 V1 over V2. Once I've got that figured out, now I just plug in my information. My pressure was 1.2 atm. I have a bit of an issue here with my volumes because I have milliliters here and liters here. So I need to get into a consistent volume unit, and I'm just going to quickly change my 345 milliliters to liters by dividing by 1,000. And that gives me 0.345 liters. So I can use that number instead. So 0.345 liters. And I'm going to divide by my second volume, which was 1.15 liters. And when I do that, my liters will cancel out, and I'll be left with atmospheres. And I will have 0.36 atm. Check my significant figures. I had 2 significant figures in this atmospheres in my pressure, so I can have 2 significant figures in my answer.